Welcome everyone. I know this was very short notice, and it's good to see so many of you here and to have Professor Hartigan here to talk with us. If you're with the Rice community or you've been watching the news, this has gathered quite a lot of attention. This event next week, or this interesting occurrence next week. And Professor Hartigan, for many of these things over the years, has actually done a really good job at putting down the basic information for us in the department as well as our broader community. And occasionally something will grab everyone's attention, and this was one of them. And so he kindly offered to give a talk, and so we kind of set it up rather hurriedly, but I think we got the information out, and it's good to see so many of you on. In case you didn't hear what we were talking about, I'll introduce Pat in a second, but in case you didn't hear what we were talking about, I will manage the Q&A, so you should see a Q&A button, and I would prefer you to use that than the chat, because it can get a little bit muddled. And Professor Hartigan's happy to take some questions during the flow of his talk if there's something you potentially need for clarification in particular. What I would suggest is if you want something in the moment based on something he says to have a little bit more explanation, then that would be great. If you have a much more general question, about astronomy in general, or some of these topics, or more to do with the planets themselves, or whatever, I would ask you perhaps to leave that to the end and put that question in the Q&A. So perhaps you can signify to me whether you're willing to wait or you need it asked right away, and then I will interrupt at a convenient moment before it gets too far ahead, and then ask the question for you. So I think those are the basic ground rules, and then we'll just go from there. And so let me introduce Professor Hartigan. Obviously, he was one of the people who was, I think he was on my search committee when I came to Rice, which was a long time ago now. So he's been at Rice for quite a bit longer. If I'm remembering, it's not
right.
No, I'm saying that you've been at Rice longer than I have. It doesn't mean that you're necessarily older than I am or otherwise. And I don't have all your bio here, Pat. I've only got a little bit about what you do. So, but his background is always been, I think, for the most part, in astronomy and physics. And I think you came to Rice from Arizona State. Is that right? Or was it a step in?
PhD in Arizona, and then I had a postdoc at Harvard Smithsonian Center for Astrophysics, and then another postdoc at UMass Amherst before I came here.
Right, so there's the fail. The speaker just introduced himself.
That's all right.
Pat's been a great colleague over the years. I'll just do the personal introduction. He's been a great colleague over the year. Very, very important for our department because of his passion and his dedication to teaching. I think we've all learned a lot from him on that front, as well as some of the great research he's been doing. So, it's always great to give him an opportunity to share his knowledge with us all. And so I won't embarrass myself further. I'll just pass it over to Pat. I'll go on video mute and sound mute, and I'll come in via sound if there's a question that from the audience. So you're sharing your screen already, so please, it's all over to you.
All right. Well, thanks, David, for that. And if there's any problem with if I'm pointing to something and you don't see what I'm pointing to, or for example, there's a little laser pointer here that should be moving around, please let me know and we'll try to work it out. Well, anyway, hello, everybody. Thank you for spending a little bit of time with me this evening and to learn about this lovely event, which is ongoing, which is this conjunction of Jupiter and Saturn. It's a beautiful sight in the western sky right now. I was just out looking at it about an hour ago. The two of them are really starting to look like a unit now. They're getting close enough together. To me, there's something about them being a little bit closer than the diameter of the full moon that just makes them look like they belong together at some level. It's almost like one of those things where instead of looking up in the sky and you say, oh, well, look, these are sort of close together. Now you're beginning to look up in the sky and say, whoa, what's that? And so I think it's definitely time to have a little discussion about kind of what these conjunctions are, how rare they are, and so on. So let's just dive into it. If I can move my I got to try to move the slide. Here we go. Okay, so this is going to be just a quick outline of what we'll go over. I want to talk what's happening, what a conjunction actually is. It turns out that there are several cycles that are associated with these, and to really understand kind of the significance of this conjunction and more in general what they are, how they are behaving, we do need to kind of dive into those cycles. So I'm going to talk about the three of those. Then we get into something that's a little bit more detailed, which is triplets. If you're interested in discussion about the Star of Bethlehem and things like that, that's something we definitely need to go over and to understand. Triplets are fairly common. They have about, kind of 15%, 10 or 15%, something like that of the conjunctions are triplets. Then we get into the part it's a little bit more difficult, which is why the planets are so close this time and how rare they are. I'll show you a new cycle that I came upon, which is this 854-year cycle of closest approaches. Down in here, now you have to kind of get into what the orbits are doing. So this part will get a little more technical. And then since there's been a lot of press about this, I felt that it was appropriate, at least for me, to touch on what sort of conjunctions may have occurred 2,000 years ago. And we can talk about that from an astronomical perspective, although I should definitely emphasize I'm not a biblical scholar. So once we get into discussions about that or anything associated with the Zoroastrian religions and kind of how they may have interpreted things, that's not my area of expertise at all. So you'll have to get somebody else in to talk about that if that's what you're interested in. And then finally, at the end, I do want to talk a little bit about what it looks like now, how to view it well, maybe some tips about photography. So if we actually look at this, if you're kind of trying to get an idea as to what's happening here. So this part should be pretty easy. This gets a little more complicated. Triples get a little more complicated. This part is actually quite complicated. And then we're going to segue to the history, which is a little bit easier, and we're going to end up with something that's easy. So if it seems like it's getting complicated in the middle and you're seeing graphs and so forth, and you're not interested in that, hang in there. We'll get into some of the more easy stuff at the end. I set it up this way because I know in this audience, we have a really wide variety of expertise. I know that we have PhDs in here, PhDs in planetary science that we're planning on coming to this. We've got people that are just very casual and are just sort of wanting to know what's happening. So my goal is that I'll hit enough different levels so that no matter who you are, you'll learn a little something about this in the next 45 minutes, however long I have. Okay, so let's go on here and we'll talk about kind of what the sky looks like. So ignore the colors for the time being. They weren't chosen by me if you don't like the colors. This is a picture of what our solar system looked like on October 3rd. So hopefully you can see my little laser pointer here. So this is what it would look like if we were in a spaceship kind of flying above the plane of the solar system. So if you just went straight up off the North Pole, went way up north and looked down, you should see something that sort of looks like this. So let's orient everybody on this. So this is the sun here, okay? And this is Mercury, here's Venus, here's Earth, Mars, Jupiter, Saturn, the orbit of Uranus is out there somewhere. And then, the outer planets, Neptune is out that way as well. So all these planets circle around counterclockwise. The Earth being here would take 1 year to go all the way around. And somebody like Venus goes around faster, like 8 months or something. Mercury goes around in about 88 days, kind of 2 years here for Mars. It takes Jupiter about 11.8 years to go around and Saturn about 29.5. So what you can tell is that everybody in close is going around a lot faster. And actually it turns out that's just a consequence of the force of gravity being fairly strong in close and less strong as you go out. So it has a 1/r² dependence. And it's that dependence that determines how rapidly these orbits or the planets move around. Okay, so let's see. So we've got the Earth here. Okay, so remember this is October 3rd, and I've got the sun here. One of the really difficult things with this business is it's kind of intuitive and easy to draw this diagram. But one of the things that's kind of hard is to try to visualize what this is actually going to look like from the Earth's perspective. So I want to spend a minute or two orienting you as to what's going on here and then explaining exactly what a conjunction is. So here we have the Earth. And so I've drawn an arrow, a black line here with an arrow at the end of it. This is a line that goes from the Earth through the sun. So it indicates the direction in the sky that the sun will appear. And so anything that's kind of near there, so for example, if my laser pointer were there, it would be really, really difficult to see that object, simply because the angle with respect to the sun is really low, really small. And by the time that it gets dark enough, so if the sun were to set and be, say, 10 degrees below the horizon, then this is also going to be below the horizon, and you're simply not going to be able to see it. So anything that's kind of in this lovely pink zone here is going to be really hard to see when the Earth's in this position. If we then move around here and kind of over towards the bluish area, these are things that are visible in the evening. So for example, on October 3rd, Jupiter was about 90 degrees away from the sky, from the sun. So it meant that it was roughly in the middle of the sky, kind of transiting when the sun would go down. So you'd see this in the evening. Anybody that's kind of over in this angle in the green is more or less up all night. And then over here, it's in the morning. Okay, so hopefully everybody's kind of following along as to how that works. So you notice now here, if I've got the Earth and I'm looking at Jupiter and I've drawn that line, you can see Saturn is to the left of Jupiter here on October 3rd. Okay, so now what I'm going to do is I'm going to move forward and I'm going to put my little dot on the Earth and I'm going to move forward to today, basically. Okay, so there's today. Okay, that's where we were, and there's today. See, so let's look at the colors first, and then we'll look at the planets. So this is the dot where Earth was on October 3rd. So you see the Earth has gone about a third of its orbit around. As it's gone a third of its orbit around, now the sun is in this direction over here, meaning that this entire area of the sky is now difficult to see because it's getting too close to the sun. So you notice that the difference between these, here Jupiter and Saturn were very high up in the sky, whereas here they're starting to get closer to the evening twilight. So it gets to be a little bit more difficult to see them now than it was back in October. Okay, so now let's look and see what Jupiter is doing. So I'm going to go here. I'm going to put my little dot on Jupiter, and we're going to see what it does. So let's just focus on what Jupiter is doing. So you can see it moves forward in its orbit, not by a lot, certainly not by as much as the Earth did, but it is moving counterclockwise in its orbit. And if I do the same thing with Saturn, you see Saturn also moves forward, but just a little bit. So Saturn's taking a longer time to go around. So the visual here is essentially, if you've been to a running track where people are doing laps. So this would be Jupiter, who's the big gas giant planet. He's sort of lumbering around. He takes 11.8 years to go around. And this is Saturn, who's hauling around the big ring, and he takes 29 years to go around. And here are you're kind of sitting in the middle of the track. I think, isn't that where the high jump people are and the like shot put people? I think they're kind of in the middle, aren't they? I don't know, I've never done that. Anyway, so if you're kind of in the middle of the track and you're watching these guys go around, you have to wait kind of for them to line up. And then Jupiter will run ahead of Saturn, and then you have to wait all the time until Jupiter loops around and catches and laps Saturn, basically. So if we go forward to here, you can see they're almost in a line. You kind of have Earth, Jupiter, and Saturn almost in a line. And the reason they're not in a line yet is that in 4 days, they will be in a line. So you see Jupiter is catching up to Saturn and they'll be aligned. This alignment of Jupiter, Saturn, and the Earth, or any sort of alignment like this, is known as a conjunction. So this is what they are. It really is that simple. You've got the planets moving around in their orbits, and if you can draw a line between the Earth and any of the objects, and they're all in one line, that's going to be a conjunction. So you might ask yourself, okay, well, these are going to then perfectly line up. But that turns out that that's not the case because the orbits are tilted just a little bit. And so orbit is tilted maybe 1 degree from that one. So if they're in the part of their orbits where this one is high or higher than this one, then even though they're lined up here in azimuth, they're kind of out of the plane they'll be. separated by a little bit. So it actually depends upon where you are in this orbit. You need to kind of find them in the spot where they're lined up in their orbits in order to have a really close conjunction. But then you also need to actually have the conjunction occurring at that position. Okay, so anyway, so this is what it will look like now. So then if we actually, it's kind of fun now. Let me put it on the Earth. Let's go forward to March. So if we go forward to March, you can see this is where the Earth was. It's now moved around here. And now kind of the zone of avoidance for the sun is here. But you notice now Jupiter and Saturn are in the purple part, and they're visible in the morning, whereas they used to be over here in the green part, visible in the evening. So what will happen is, from our perspective, is that both of these planets are kind of sinking towards the sun, and they will eventually pop out on the other side in the morning. And what's happening is essentially Saturn looks like it's moving past Jupiter, or Jupiter moving past Saturn, either way. So let's look at this. So here, if we start out in October, from our vantage point, Jupiter is to the right of Saturn. And then here, you can see from our vantage point, Jupiter is to the left of Saturn. So in our visual, they essentially just cross one another in the sky, and that position of closest approach is going to be on the 21st. Okay, so that's pretty much that. So let's go on now. So this is now a picture of a conjunction where I've just sort of lined them up. So I've lined up the Earth here is in blue. Here's Jupiter and here's Saturn. I've got little rings that I put on there. I'm very proud of those, by the way. And I've got a little ticker up here. And so I'm going to run this forward in about 120 years so you can watch what happens. So every time the Earth moves around, this ticker is going to increase by 1 year. And Jupiter will take 11.8 and Saturn will take 29 to go around. So let's see if I can get this to work. Okay, there's 1 year, 2 years, and so forth. Okay, remember we started them up here at C0, so that was conjunction 0. Okay, let's watch them. And you can see they're going to line up right there. So their first conjunction is sort of going to occur over here. Now, I've only drawn the lines with respect to the sun. And so if you want to get detailed, you have to kind of figure out where the Earth is in there to get that lined up perfectly. But roughly, that's where they're going to be. And the second one is up there. All right, now everybody look at this and guess where the third one's going to be. Not quite fair because I already gave you the answer, putting in the little dotted lines, but you know. Round and round we go, and in 60 years, we're there. So you can see that there are these cycles, and that every 20 years you get a conjunction, but it's in a different part of the sky. And interestingly enough, these conjunctions, here comes number 4, there. These conjunctions tend to occur in these triangular patterns in the sky for these two planets. Notice that the alignment isn't perfect. So after 60 years, you've now moved to this conjunction point. And after 120 years, well, I'm giving away the answer. We're kind of coming up on 120. The next one is going to kind of be here. So what you have is these kind of triangular spots in the sky, and the whole triangle gradually moves forward. Here comes the last conjunction right there. Yeah. Okay, so if I can try to make this work, let me see if I can get back to conjunction 1. It's almost right there. Okay, that was pretty good, actually. All right, so here's kind of where conjunction 1 is with respect to the sun. You notice it doesn't quite line up with the Earth. You'd have to wait for Jupiter to go by a little bit more. But more or less, it's sort of there. But you notice that which side the Earth is on. The Earth is on the right side, okay? Now I'm going to try to move forward and see if I can get to conjunction 4, and we'll see where the Earth goes. Okay, so here we are with the Earth on the right side. So 60 years later, I'm going to go here, if I can get that to not screw up. Oh, almost. Get in there. Perfect. Okay, so here you can see the Earth is on the left side. So the point is that every 60 years, even though you're sort of in the same spot in the sky, the Earth is on one side. Your Earth will be on this side for one, and the Earth is on the other side for the next one. So in some sense, it makes sense to have these things, talk about these things in terms of 120-year cycles. If you do 60-year cycles, then in one of them, it's going to be in the morning and the other one is going to be in the evening and so forth. But generally what we would expect is we should expect to get a cycle, a conjunction between Jupiter and Saturn once every 20 years. And then once every 60 years, it could kind of come back to the same spot in the sky. And once every 120 years, it will come back to roughly the same spot in the sky and also the same spot with respect to the sun. So either morning or evening. Okay, so that's kind of described here. Oh, and by the way, this 59.58, that 0.58 is the problem, because even though after you've gone 60 years, now you've got half of a year, which means the Earth has moved to the other side of its orbit. Right? All right, so you may ask, well, this is kind of unusual. Why did they look like this? And the answer is that you have almost exactly a 5-to-2 orbital resonance between Jupiter and Saturn. By that, I mean, if you take Jupiter's period and you multiply it by 5, it's 59 years. It's very close to 2 Saturn periods. And so whenever you've got this sort of 5-to-2 resonance, you end up getting this sort of a triangle thing, where every time you get a conjunction, it moves forward this angle, which is 242 degrees pretty much. You get the first conjunction there, you go 240 degrees, this one, you get the next one, and so on. So that's kind of how that works. And so this summarizes this, and I've just put this up so that we can come back to this if we need to when we're talking about it later. So remember, we started out with the conjunction here, the first one being here, and then after we zipped around, we had the third one being here with the Earth being on this side, and then the sixth one being here with the Earth being at this point. So we'll come back to this as we need to. So try to keep this in your head as we go forward. All right, so let's see where we are in the talk. So we've talked about what's happening.
Oh, Pat, yep. Sorry, I thought I'd unmuted. We do, before you move on, we do have a question.
Sure.
From someone going by the name of Captain Joy, but I think Pat Rife knows who
Hello,
he is.
Captain.
But, so how common is that 5-to-2 resonance, and is it only Jupiter and Saturn?
You do see these types of resonances in other systems. One of the main ones is the asteroid belt, where you will have Kirkwood gaps, for example, are 2-to-1 resonance between the motion of the asteroids and then the motion of Jupiter. I would have to look to see if the 5-2 resonance is visible in the Kirkwood gaps. I'm sure somebody can Google it faster than I can talk about it. But these types of integer ratios are quite common for producing. What they do is they produce either perturbations, which will yank things out of that orbit, or they'll put them back into an orbit. I don't think this is a random thing. I would suspect that the reason why they are in this 5-to-2 probably has something to do with very long-term solar system dynamics. But I know we have some planetary scientists on this talk, so maybe they can tell me something about that at the end here. But these types of resonances that are sort of these low integer resonances make a difference. They're the sort of thing that, for example, causes the gaps in Saturn's rings also, is that they have resonances with the orbits of the moons. And so those types of, basically what happens is every time that the thing goes around, it provides a little kick, which will perturb you one way or the other. But this whole business about planetary dynamics is a very complicated and very interesting thing. It has to do maybe with the overall formation of the Earth. I'm not going to go into that unless somebody asks me, but you can ask me about that if you want at the end. But yeah, good and potentially complicated question. All right, so anyway, so this is where we are. So question is, what's happening? And so what's happening is they're just in a line. We've talked about the 20-year cycle. There's a 60-year cycle, which brings it back to the same spot, and 120-year if we're actually looking at the different morning, evening sort of things. So I'm going to adopt this 120-year thing. So it means that in my cycles, I'm going to have six different cycles that are ongoing at any given time. And you simply cycle between them. You go cycle 1 to 2, 3, 4, 5, 6, and then you come back to cycle 1 after 120 years. Anyway, so here's where we are. So now we need to talk a little bit about triplets, and then we need to dive into the weeds before we look at the history. Okay, so let's talk about triplets. All right, so triplets come out of this whole idea, or triple conjunctions, come out of this whole idea of retrograde motion. So we need to understand that a little bit if you haven't seen this before. So what retrograde motion is I've sort of indicated it here. It has to do with the apparent motion of an outer planet when seen by an inner planet like the Earth. So I put the Earth in here, and you notice that the Earth is going around. I've got it sort of regular intervals as it's going around. And I have my outer planet also doing that, going on regular intervals as it's going around. And the outer planet, of course, is going slower. So it's taking longer to go around. So this arc for a given time interval is smaller. So these little arcs are bigger than this arc, for example. So all I've done here is I've drawn lines. And so I've drawn a line between this one and this one, this one and that one, this one, and so forth. So it looks pretty simple from the standpoint of an observer looking up above the solar system. But remember, when you're in the solar system, in order to figure out where this planet looks in the sky, you actually have to look at where this angle is. And so here what we've got is we've got kind of minus 17 degrees, where minus I've decided I'm going to define as being when the arrow points a little bit to the left. 0, like here, is going to be when it points straight down. Positive is when it points to the right a little bit. And so you can see what happens to the angle as it starts out negative. It kind of gets to be almost 0 here as it's pointing straight down. And then here, it looks like it gets positive again. And then here it's 0, it goes negative, and then positive. So if I simply plot these angles, so like this longitude, and that's what's on this axis, I plot this on the sky, I'm going to get a trace that kind of looks like this, is that it's going to go in, it's going to turn around, go back, and go this way. So this backward motion is known as retrograde motion. Now, whether or not it does that just in a line, or if it kind of does it like I have here, like a little snake, depends upon what the inclinations are. So if I've got the inclination tilted a little bit, and I'm going down from low to high, then it will kind of do that gradual low to high thing as it's doing its motion. But the main point is that between C and E here, it will appear that the object is going backwards. Now, remember, we have 2 outer planets here. We've got Jupiter and we've got Saturn. So they're both going to retrograde. Now, the angle on the sky is going to be bigger if the object is in closer. You can imagine that if I had somebody in here, these angles are probably going to swing around a lot more than if I've got an object that's orbiting way out here. So kind of this distance, if you will, is bigger for Jupiter than it's going to be for Saturn. Alternatively, though, Saturn actually is retrograde longer than Jupiter, because in the limit that you have an object going to infinity, it's retrograde over the whole bottom part of the orbit. But anyway, that's the idea of retrograde. So if you're watching the object move, that's what it does in the sky.
So Pat, can I ask a question from a high school student?
Of course.
I'm not sure. I maybe this is from Darla, and I'm maybe not fully understanding what she's asking. But she wants to know, for that, going back to the 5.2 resonance, she's asking if that occurs for both planets, and I think it might help to sort of answer that in terms of the system, if I'm understanding her question.
Yes, it's right. A system. So let's go back to this picture, which I knew was going to be useful. By a 5.2 resonance, I mean that you have to have 2 objects that you're considering resonance for. And so in this case, we're considering a resonance between Jupiter and Saturn. So we simply say, all right, how many times does it take Jupiter to go around for the amount of times it takes Saturn to go around? So if you actually look at their rates are Saturn's rate of going around is about, or Jupiter's rate of going around is 2.5 times that of Saturn. So that means that every time Jupiter goes around 5 times, 3, 4, 5, Saturn will have looped around twice. 1, 2. So it's kind of how I feel when I'm swimming in the pool. I'm like the slow guy that's taken 2 laps and somebody's zipping by me 5 times. And then, you finally get to the end of the lane, and then you started out at the same point, but then you get lapped a bunch of times. And then at the end of it, you've done 2 and they've done 5. Is the right way to think about it. So that's what these numbers are, is they relate to their periods. So if you take 5 times the 11.8, so 5 times that number is about equal to 2 times that. Not exactly, but pretty close. So hopefully that helped. Okay, so let me move on then. So we're talking about retrograde motion. and triplets. So I'm going to show you why a triplet occurs. So in order for you to have a triplet, you kind of need to have the conjunction, which is where this is lined up here, be when the objects are opposite in the sky from the sun. So I'm just going to show you a movie and then I'm going to narrate it quickly. What we want for a conjunction is we want this line to not be bent. So the line between the Earth, Jupiter, and Saturn needs to be a straight line rather than a bent one. Because here, Jupiter would appear to the right of Saturn. So I'm going to say now, now, and now when this thing goes and is lined up. Okay, so everybody ready, I hope? Now, now, now. And I'm going to let the simulation go another year until it's around so that you can see in the following year there was no conjunction. Okay, so let's see if I can do that again. Boom, there's the first one. There's the second one. And there's the third one. And now if we let it go another year, there's no conjunction anymore. So then now we have to wait all the time for Jupiter to, moves around 1 2/3 times, and Saturn has to go all the way over here, and your next conjunction will be over here then. So the point is that every once in a while, when you've got these conjunctions that are kind of occurring in the middle of the night, they will occur in sets of 3. And those are your triplet conjunctions. See anything else I want to do with that? Nope. Okay, so this is another way of visualizing a triplet. So, and this will help us understand how the sequences move. So we're starting to get a little bit more detailed now, and we're going to get even more detailed, and then we'll back away from it. So here we are in 1563, and then we're going to go ahead 120 years to here where there was a triplet, and then 120 years more where there's here. What happened to my little laser pointer? Okay, here it is. All right, so this is all part of the same sequence. So here's one sequence where we're going in. Now this is longitude. So this is that thing that we were looking at. Go back. That's this angle, okay? So this is the longitude. Remember, the longitudes have got to line up before you have a conjunction.
So Pat, sorry, I'm just getting some other questions, and I think they're easier to answer with what you just said as opposed to what you're about to say. Okay. Blanca is asking, let me ask the 3 together, or maybe the first 2 and then the other one separately. So there's 3 questions. So Blanca asks, are all the calculations based on circular orbits instead of elliptical ones? And Lolly asks, are we having a triplet this conjunction? And then I'll ask one more after you've answered those.
These are, I'm showing you them on circular orbits so that you can see them. When we actually get down to doing the measurements and showing you where the conjunctions occur, you have to take into account all of the aspects of the orbit, including the inclination and the eccentricity, and the fact that the planets move faster when they're in closer. Remember, I warned you that we're going to get more detailed. Well, guess what those details are? It's exactly those pieces. So we're coming to the nastiness of the elliptical orbits. But I don't want to get there yet because it gets to be too complicated. This is a much more basic phenomena. The triplet phenomena is independent of whether or not you have elliptical orbits. But
and he's saying
it'll get nasty soon.
And he's saying all that just to show you that astronomers are really smart. They're not just, physicists always like to think they are smart, but astronomers are really smart. So the question was, are we having a triplet this conjunction?
We are not having a triplet this conjunction.
And that was from Lolly. And then there's a question from an anonymous attendee. Are there planets in our solar system in a closer to exact integer resonance? And maybe that's something you might want to save for the end, I guess. But we'll come back to it.
Not that I know of, but I haven't looked at all of them either. So there's the Earth and Venus actually have a really interesting 8-to-5 resonance, actually. But I've never been able to figure that one out because there shouldn't be enough gravitational perturbations there to make that to matter with that. But with these guys, they're pretty massive, so you would expect their perturbations might matter. Okay, so anyway,
Thank you.
so let's go forward. So thank you for those. It's great. All right, so this is a little bit more complicated graph, but what we've got here is now time. And these are our retrograde orbits. So for example, this is Jupiter. So it's going forward in longitude, goes backward and then forward. Here's Saturn, goes forward, backwards, and forwards. So you can see this particular conjunction is only in the morning. So the evening, kind of midnight is here. So this one will occur in the morning. And then if we come back 120 years later, they're not exactly in the same spot. And relative to one another, the Jupiter is shifted down a little bit. So here you get a triplet. So here you get a morning, you get one kind of in the middle of the night, and then you get an evening one. And then after another 120 years, this thing has shifted so that you miss the morning one and you only get an evening one. So there's a general trend within each cycle is that you should kind of go from the morning to a triplet to evening. And then these evenings will gradually get closer to the sun and then flip around in the morning again. So we should expect to see something like that, we hope. Okay, so that's enough theory. So it's time to actually look at some data and to see whether or not any of this stuff makes any sense. So let's see if we can do that here. I think I should have a pen. Yes, here's my pen. Okay, so we've gone through quite a bit of stuff already. So let's try to see if we can understand it. Let's just look at the dates. So this has everything in there, including the elliptical orbits, the inclination, everything, okay? So we just want to look at the dates. So let's start out with a conjunction here in 1206. That one. If we move forward, the next conjunction is in 20 years. The next one after that is in 20, 20, 20. This is looking really good, right? Uh-oh, 1305. We got 3 in a row. But that's our triplet. Okay, so that's good. 20 years, 20 years, 20, 20, 20. Here's another triplet. Okay, 20, 20, 20. Okay, so we got this figured out. So it kind of goes 20 years and then a triplet, and the triplets kind of look like they're weird. They're not spaced evenly necessarily, but remember there's all these different cycles. So this was a triplet which kind of occurred in series 1. And interestingly enough, that same series produced 2 triplets in a row. And then after a while, it's kind of series number 2 produces them and so forth. So we need to kind of look at what's going on with all the triplet stuff. But generally what happens is you do have this 20-year thing and you've got the triplets. All right, so the other thing we want to look at is the longitude. So here's a longitude, which is 66. After 60 years, it moves up to 79. After 60 more years, it's 87. 60 more years, it's 94, and they all do that. So every 60 years, the longitude is moving forward, but we knew that anyway, right? Because we looked at this thing. And that's this business, is every 60 years, it's slowly moving forward in longitude. Okay, so that's what's going on with that.
And so, Pat, I have a question on that from, I think it's Chris Captain Joy again, who he's basically saying this data that you have listed here, is it based on models or measurements from the time? He's assuming it's models.
Yeah, these are all based on the latest and greatest planetary ephemeris from the Jet Propulsion Laboratory. So this is how you actually have to go and calculate these things. And that's far better actually than observations at the time, because observation of the time had enough uncertainty that it doesn't really constrain things. But to the degree that we can actually launch satellites and have them end up at the planet, JPL cares a lot about that because it would suck to launch a mission and not actually get there. They have very good planetary predictions. So I think everybody is very confident as to how good these predictions are. However, towards the end of the talk, I'm going to move you forward and backward 10,000 years. Once you start doing that, then the small errors in the predictions may begin to slowly accumulate. And so you really need to have the best possible ephemeris to be able to calculate those. But nobody disagrees about any of these. Plus or minus a few thousand years, our planetary calculations are really good at this point. All right, so let's do a couple other things here, just noticing that for the degrees from the sun. So you can see this one is in the evening, positive ones are in the evening, and then it shifts to morning, okay? And then This evening one is kind of shifted all the way around the sun, and then this one is now a triplet. So you have three of them, one in the morning, one kind of in the middle of the sky, and then one in the evening. So these are degrees from the sun. So if it's 23 degrees, for example, it's 23 degrees up in the western sky. Minus 23 degrees would be up in the eastern sky. So I put a little thing here as to whether or not it's easily visible. You really need to have this greater than about 20 degrees to have a shot at seeing it. When you have something like ours, which is 30 degrees, it's pretty easy for some of us. It will be a little bit more difficult for other people. Anything above 30 degrees is super easy. So let's go forward now, same sort of thing. Let's find ours. Ours is here. Okay. So here we are, we're at 30 degrees, which is pretty easy to see. I'll put a question mark there, although you got to do a little bit of work to see it. But the other thing that's interesting about ours is it's very close. So let me go backward. So this is a separation in arc minutes. So to give you some sort of a scale, 30 arc minutes is the size of the full moon, okay? And as we saw kind of tonight, that's kind of what the separation is between these guys. So anything that's less than 30 starts to really look impressive. Anything that's more than 30, it's kind of a lot less impressive, at least from my point of view. So this one is really close. It's going to end up getting only 1/5 the diameter of the full moon apart. That's what its projected separation is going to be on Monday. So it's a spectacular sight. So if we go this way in the past and we see, what do we got we got nobody here. Okay, we have to go to the previous slide and we go up, got nobody, got nothing going on, nothing. Oh, here we go. So this one is in 1623. Is the last one that was this close, but that's only 13 degrees away from the sun. There's like no way you're going to see that. It's too close, because by the time the sun sets, the planets are already really, really low, and Saturn's not all that bright anyway, so you're not going to be able to see that one. So we have to keep on going. This one almost is as good as ours, not quite. We go back, backing it up, Charles Barkley, backing it up, until we get to this one, which is March 4th, the year 1226. These things would have been 3 times closer than what they appear to us. So it may have even appeared as a single object. But that's the last time anybody has seen these things this close. So when you go out on Monday and you see this, I mean, you've got a historical connection to people 800 years ago in the year 1226. Just to give you some sense, this is when Genghis Khan was roaming around Asia. You had the Crusades going on. And you may have heard of Notre Dame Cathedral, the one that had that horrible fire. This is when it was being built. So it's really very interesting, I think, to have this kind of long-term connections between things. Another interesting thing about this, if we go forward in time, you notice in only 60 years, in the year 2080, we have another one, which is almost exactly the same as ours. It's separated from the sun really well, but it's in the morning because it's 60 years away. It's part of that other series. And so the cool thing about that is that, you know, if you're 20 years old now, you can go out and see this one. And when you're 80, you can go out and you have to promise me, any 20-year-olds here, when you're 80, you have to go out in the morning sky and see it. And maybe think back to this lecture or think back to these times, which will either seem very chaotic or very quaint, maybe depending upon what's happening between here and here. But the point is that any time that you have, you know, if you live 80 years, you're going to see about 4 of these conjunctions. They really are fairly rare. And most of them are very wide, like a degree apart or something, or they're too close to the sun or something like that. But so this one is really quite special that way. Okay, so let me glance through a couple of things and we'll do a couple more complicated plots and we'll talk about the history. So once again, with the longitude, remember that for a given series, let's pick, would be a good one. Let's pick this one, say. So here we've got between series 1 and series 4, these are ones that are separated by 60 years. They have very similar longitudes, but those longitudes slowly increase. And so we go from kind of a morning one to an evening one, morning, evening. Then there's a triplet. And then after the triplets, the morning ones become the evening ones become the morning ones, and they alternate till you get another triplet. They alternate, you get another triplet, and so on. So if you're interested in getting a particular point in the orbit, then the separation is kind of between, say, there and there. And that's about 800 years or so. 800-ish years.
And Pat?
Yep.
We have a quick question from Kim asking, what is a series in your plot here? What do you mean by a
so
series?
that was back when we were talking about the individual series. So let's see if I can get there quickly. So we had these different cycles, right? The 20-year cycle, the 60-year cycle, and the 120-year cycle. I've been talking about a series as being one of these 120-year cycles. So that's why there's 6 of them. So just to remind you, if you start out with a conjunction here, that'd be like series 1 or something. Okay. And then you come over, well, let's make that one series. Of course, I labeled this one 0. But so yeah, okay, let's call this series 0 then. So this would be series 0. And then the next conjunction over here, that would be number 1. Next conjunction is number 2. You know, number 3 is here. Number 4 would be here. Number 5 would be there. And then number 6, which I'm calling the same as number 0, is kind of part of the same series. So this conjunction here is part of the same series as this conjunction because they're roughly in the same part of the sky. The Earth is roughly, here it is for number 6, here it is for number 0. So they're roughly in the same part of the orbit for the Earth, and they're in the same part of the sky. So each one of these things that's kind of 120 years apart, I'm calling one series. So hopefully that's helpful.
So Pat, I do have some other questions coming in. Are you in a good position to answer them, or do you want to?
I don't know. I mean, we've got a couple more complicated things, and then we're going to do history. So you tell me.
Let's see. I've already got one on hold. I'm going to leave, Mark, I'm going to leave your question to the end too, since it refers to an historical date. So that's a good excuse for leaving it. And then Darla's just wondering what would happen if Jupiter and Saturn never coincide again. But again, that might be something that we can tap on to a question at the end. So let me save both of these for later and let you go on.
Okay. So remember, we're getting to the complicated part with more graphs and things, and then we'll segue to more of the historical part, and I'll talk about what this is going to look like, and we'll talk about photos and so on. But anyway, if you cared about a particular longitude, so like suppose you cared about this longitude, then you know the series are kind of going to be in that part of the sky every 800-ish years or something. The reason that I pull this, that I mention this, is the following: is that this is now a more complicated graph. And this is one where I've got the orbits of the planets. So this is the orbit of Saturn on the outside, Jupiter on the inside. And I've indicated where they are in terms of coming up out of the plane. So this little symbol here is a longitude of indicating an ascending node. This one is descending node. And what that means is that the red part of, so if the plane of the, so if we put the Earth's orbit in here, and then we make a plane around it, and then we put in these other orbits and we tilt them just a little bit, what you're going to find is that sometimes Jupiter's orbit is below the plane of the Earth's, and sometimes it's above. And this red part is where it's above. And the same thing for Saturn. So you notice some interesting things. First of all, they're kind of tilted in the same way, in the sense that both Jupiter and Saturn come up out of the Earth's plane of the orbit in about the same spot. And the reason for that is just that the Earth's orbit is tilted relative to these guys. And so that kind of makes these positions the same. But the point is that pretty much anything that's in this area, if the conjunction occurs there, or if it occurs here, either of those two areas is going to be a pretty close conjunction, because these things are then not going to be up out of the plane. If you're over here, it's going to be lousy, because if they're tilted up by a degree, you know, there's a degree difference in the tilts between these. So they're never going to get closer than about a degree. So that's why there's a lot of conjunctions that are kind of like a degree apart, and only a few of them that are really close. And so, and these things then should have some sort of cycle of roughly 800-ish years, one would think. Okay. So if you pick this longitude, then every 800-ish years, you should sort of have things lining up. And of course, you would then have one 180 degrees from that, which would kind of be here. And so, you know, you would have these guys. So if you look for
In
close
fact,
conjunctions, it's sort of every 400 years or so, and then a given sequence every 800 years.
yeah, there's just a quick question from Michael asking how much of this assumes calculus. Can you do it without?
Oh, all of this requires you actually following the positions of the planets in their elliptical orbits. And that's actually a really hard problem. And you have to use Kepler's equation, which is a transcendental equation, which has to do with all sorts of interesting angles and so on. So in order to really figure out the orbits and to do them well, I mean, that's all kind of a calculus thing, although I will say that Kepler was able to do it without calculus because he was a master geometry person. But if you look at some of his calculations, you kind of go, oh my goodness, look at all those triangles and lines and everything. It's hard to do if you don't, it's much easier to do if you know like the forces and so forth, which is Newton's law.
And I think he spent 20 years drawing triangles, right?
Yeah, probably. Well, he's actually kind of a mystic as well, because he was interested in astrology and so forth. We may talk about that a little bit when we get to the Star of Bethlehem, which is coming right up. But anyway, so let's take a look at the closest conjunctions now. So this is the closest conjunctions in this 3,000-year interval. Here we are. So these are ordered according to separation, okay? So larger separations go down this way. So here we are. So we're doing pretty well, right? The next closest one is the one in 2080. Here's one that's 400 years away, roughly. So that's in a longitude. Here's the longitudes are about 300. Here they're about 120 or so. And here's more of them that are 300. Okay. So it's only in those two spots, essentially, where you're getting a lot of these really close approaches. But anyway, so here we are. And then we go backwards. So 400 years from now, there'll be a good one. This was one that I said that we couldn't see. This one is another one also we couldn't see because it's too close. This one is the one 2874, which is coming up about 800 years from now, which will be really good. And this is the 1226 one that I talked about. And then the winner is actually in the reign of Justinian I of Rome back in 372 AD. And that was 1.9 arc minutes. But even these aren't close enough to have the diffs overlap. You need something less than about 0.4 to do that. But anyway, this will give you an idea that we are, in fact, pretty rare. So just to give you an idea, this is what the 372 conjunction would have looked like in a telescope if they had them back then, which of course they don't. And I just mentioned that even if you don't have a close approach, you can have pretty things. So for example, in 20 years, there'll be this nice isosceles triangle and the moon will be in the front. So you can always find stuff like this going on. That's quite common. Okay, so let's talk about how we can get the closest conjunctions and then we'll go on to the history. So if you want an identical conjunction, so suppose you have something that's really close and you've got them here, here, and here. What you want is if you wanted to reproduce that almost exactly, what you would want to do is, first of all, they have to line up, and that happens every 19.86 years. So those are your options. Like, okay, your first 19.86 years, it's here. Your second one, second one is up here. None of those are any good. The third one is sort of close, but maybe it's not close enough. Maybe you really want these things lined up. And so, these are your options. So it has to be some integral number of 19.86 years. The other thing is that the Earth needs to be in the same place in its orbit. And the final thing is you need to have this thing be the same longitude in the sky. Well, it turns out that this little, I did my own little Kepler numerical thing here, is that if you have 43 of these synodic periods, so 43 of these 19.86 years, it's equal to 856 years almost exactly to within 1.3 days. So what this means is after 43 of these, the Earth is almost exactly in the same spot. The other interesting thing is that if you take 43 times this 242 degrees, that's almost exactly equal to 29 revolutions. These things will be as close as 2 degrees apart. So what this means is that if we look at really close conjunctions and we subtract 854 years, they ought to be almost exactly lined up. And so I've done that here, and sure enough, it worked out. So look at this. Here we have ours. If we go back 854 years, almost exactly to the day, it's this one. which is 9 arc minutes away, and 854 more years is this one. So here's some of the other ones. This is the one in 1226 that we talked about. 854 years is 372. And this one's here in 2080. This extra 2 weeks in here is because they changed from the calendars, Julian to Gregorian calendars. There's extra 2 weeks there in the 1500s. So this is pretty cool. There's some interesting things here associated with that. And so I point these out here. And one of the things that I found was this amazing one. Like, okay, if I go this far in the future, like to 8674, it looks like they're super close. Now, remember, you have to actually try to believe these ephemerises that way. But I looked forward and backward for 10,000 years, and here's what I find. So I gave these guys little names. So let's see if this works. So the first one here in the upper left, okay, everybody look at that one. That's the name I gave it. Okay, and now the one in the upper right. I can't see if anybody's laughing at my bad jokes. One in the lower left. Okay, and the final one in the lower right. Right. All right. So anyway, it's kind of fun to look at these. So it shows you that in principle, the planets could in fact overlap. But this is, in prehistorical times, 7,000 BC, something like that. So, 9,000 years ago. This is 5,000 years in the future. So it's hard to know. So the last complicated graph, which I'm not going to go into, but just to talk about the elliptical orbits. One of the things that we notice is that, let's pick a big given series here. So this series, you go from evening to morning, you get a triplet. Evening to morning, you get a triplet. That all makes sense. Weird thing here is you get 2 triplets in a row, and then it like gets stuck in the evening. It sits in the evening for a long time before it comes down. Series 4, which is 60 years apart, does the same thing, goes evening to morning, but they're kind of switched off. So that every time that this thing is at 0, you get a triplet with the other one, and vice versa. But you see, this one gets stuck in the morning. So these things aren't perfectly periodic. They're kind of icky. And the reason that they're so complicated has to do with elliptical orbits, is that the planets aren't moving around in this nice little circular thing. They actually move faster in some places and slower in others. And if you really want to understand that, you have to go all the way back to this diagram. Where's the one? Go back to this one, which shows you where they're at their closest approach, where they're furthest away, and those things are different. So if you really dive in and you want to try to understand that level of detail, you have to put in all the elliptical orbits. And that's too detailed. I'm going to skip that. I can hear you guys all saying thank you. All right, so let's go on to the last little bit and then we'll be done. I do want to talk a little bit about the historical aspects, especially for 2,000 years ago, because this has received a lot of press recently regarding Star of Bethlehem and so forth. So what I'm going to do here is essentially just show you the data and more or less let you make your own conclusions about things. This whole idea about Jupiter and Saturn being part of the Star of Bethlehem, as far as I can tell, seems to have originated back in Kepler's times, because he was aware of these triangles and that the triangles of the conjunctions were moving. And he tried to attribute some significance perhaps to the constellation that they were in, and so on. But I want to look at it a little bit more from a modern perspective, in the sense that if you were to go back to that time, would you have seen something spectacular? And I think, people have talked about, okay, your usual greeting card thing is that you have some brilliant star hanging over the manger. And the problem with that, of course, is that if you did have, that does happen in the sense that you do have a very bright stars that sometimes appear in the sky if a star is exploding, say with a nova or a supernova. But when those happen, those are recorded around the world, and they also leave remnants that we can look at and then look at their expansion velocities and then go backward in time to figure out when they were. And the results seem to indicate that there was nothing that was happening at that time. So the idea of having a brilliant star at that point doesn't pan out. if you wanted to then say, okay, maybe that wasn't that, but maybe it was just a especially spectacular conjunction, something like what we're seeing now, that's something that we can also address. What we can't address really well, unless you want to get into the biblical scholar aspect of things and studying the different types of religions, is, does the constellation matter? Does it matter if you're in the house of Aquarius or the house of Pisces? Those things are a lot more astrological in nature, and that isn't anything that I can address. But what we can address is we can ask ourselves, if we went back to those times and looked up in the sky, would we have seen something super spectacular that's very unusual? And so that's what I'm going to talk about now, because there's been two things that have sort of been put forward that may fall into that category. And I'll show you the data and I'll let you make your own conclusions about them.
So Pat, before you go on, I have a question from Bill asking if the early astronomers and potentially the Magi, would they have known about these conjunctions? Wouldn't they have been? Did they have the knowledge to know when these conjunctions were going to happen?
Yeah, certainly they would have if they were watching the skies long enough. These cycles, people knew about the planets well back in the prehistoric times. They were originally called wanderers because they would move relative to the stars. So the planets, at least the visible ones, Mercury, Venus, Mars, Jupiter, and Saturn, they were all known to the ancient astronomers. And that, I think, probably even predates written history. So people have been certainly watching this to try to figure out portents and cast horoscopes and look at the future and that sort of thing. They've been doing that for a long time. Astronomers used to, when nobody wanted to pay us to do astronomy, we would cast horoscopes for the king. It's kind of a cash cow for us. Although it was dangerous too, because if you predicted a solar eclipse and it didn't happen or you missed one, you needed to leave town pretty quickly. But yes, they would have known that. But the question is, what degree would they have really, really precise measurements? Probably nowhere near what we have, certainly. They would have been able to get some idea as to when these things are coming together, but whether or not they would have been able to predict how close they are, that's a much more difficult calculation. And they wouldn't have gotten it exactly. They would have maybe said, okay, well, this year we kind of expect something to happen, and they might have watched that. But they were pretty good. These guys spent a lot of time watching the stars. Okay, so let's do the first thing first. Let's look at Jupiter and Saturn, which is oftentimes called a grand conjunction or great conjunction. I don't like either of those terms because not all of these things are all that great, even though they're called great conjunctions. But Kepler coined the term, and he's way more famous than me, so there you go. All right, so I've got written down for you here, just for your own perusal, all of the conjunctions in kind of a 260-year interval between Jupiter and Saturn. All right, the ones that are in orange, I highlighted because they are particularly kind of interesting looking. The ones that is in yellow is the one that's usually talked about as being a possibility for your Star of Bethlehem. That's in 7 BCE. Just to remind you, most biblical scholars put the birth of Jesus somewhere between 4 and 6 BC. There may be a little bit of a range in that, but it's kind of that way. So if we let's just look at the separations here. So in this period, there's no doubt the best separation was in 86 BC. That one is even better than ours. It would have been beautiful. It would have been pretty close to the sun. It would have been kind of hard to see. But if you had good skies, you might be able to pick that one out. In my mind, the one that really stands out is this. This is a beautiful triplet conjunction. So you get 3 of them in a year, and they're closer together than what you would see tonight. So they're only 10 to 14 arc minutes. Not as close as what we're going to see Monday, but really close together. So this would have been outstanding. And if this were happening now, we'd be making a big deal out of it, because there would be 3 of them in a row and they would be super good. A lot of them end up being like a degree, right? This one isn't too bad. It's 16. This one's kind of like ours. It's about the same angle, although it's not going to be as close. And then there's this triplet, which is not very good in terms of how close they are, but it is a triplet. And then there's a bunch of them. There's a few of them like this one you can't see because it's too close to the sun and so on. Okay, so that's the data. Just to put this in perspective for you, we actually had a recent triplet, if you notice. That was in 1981. And I watched it because I've been watching the skies for over 50 years. So this was one that I thought it would be fun to kind of watch. It's basically my first year of graduate school. And, when I watched it, I thought, oh, that's kind of neat. Jupiter and Saturn are kind of close together in the sky. Just for reference, this is the full moon, size of the full moon. So they're about a degree apart. And if you were to go back to 7 BCE, you would have had a very similar experience. They've been about the same degree apart sort of thing. So nowhere near even as close as they were tonight. And there's something, at least from my point of view, if I'm looking at these things, that if I see them and they're kind of less than the size of the full moon, they really look like a unit. Once you get bigger than that, then they're just kind of close together in the sky. You've probably never heard of the 1981 conjunctions, and probably for good reason, although I thought they were sort of cool when they were happening. So I think if you went back to 7 BC and you looked up in the sky, you would sort of see these things in the same part of the sky, but I don't think that you would, at least I wouldn't think that it would be anything too spectacular. For example, this is what ours is going to look like in comparison. So this is how close ours are, and this is the one in 7 BC. Okay, so that's the data, so you can make your own conclusions about that. Another possibility has been this really interesting conjunction of Jupiter and Venus, which occurred in June 17th, 2 BCE. And Jupiter and Venus conjunctions are a little different because they're over quicker. They happen very quickly, just because the planets are moving around a lot faster. And so you actually sometimes need to be in the right part of the world to be able to see these right. So if you actually look at Palestine back then, these things would have emerged to a single object. So it would have been quite an interesting sight in the sense that if you looked at this, you would just see one object. Now, it wouldn't suddenly get brighter. You would think that it would because there's two of them there, but Jupiter is so much fainter than Venus that it would basically look like one night you would see Jupiter and Venus separated by a little more than the full moon. The next night, Jupiter would have disappeared, and all you would have seen would be something that looks like Venus. And then the next night, it would be Venus would kind of pop over on the other side. So this is quite unique. It's up in the west at sunset. In terms of using this for a Star of Bethlehem, the date seems a little late because Herod is supposed to have died in 4 BC. And to make the story work, you kind of need to have Herod alive. I will say that Jupiter, this one is, I think, quite impressive. If this were happening now, we would make a fairly big deal out of it. Nonetheless, Venus-Jupiter conjunctions do happen every 13 months. There was another one, I think, about 42 years after this, where they were very, very close. Every once in a while, Venus will actually transit Jupiter. That happens about once every 300 years. So these things do happen. And of course, in any given time interval, you can find something unusual too. But this one, I think, was definitely more interesting and unusual than the Jupiter-Saturn one to our modern eyes. But, if you put in the astrology parts of it, like maybe it matters more to you if it's in Pisces than if it's in Taurus, because Pisces means something different to you than Taurus, then that's a different question altogether. All right, well, enough of this stuff. I'm sure you're tired of this at this point. So let's actually look at what we're going to see, and then we'll end and field some questions. So just in terms of the basics of it, this is what it should look like. For those of you who have seen it, it's beautiful now, and you should go out there and look at it. Tomorrow night looks like it should be clear. Actually Monday looks good. I think we're supposed to get some rain in between. But yeah, watch this over the course of the next few nights, and you should see the planets getting closer and closer together. I've never seen a conjunction this close, so it's going to be fun for me to see it also. The separation, as you can see, is about 30 degrees. Obviously, that's not going to change where you are. That separation stays constant no matter where you are on the Earth. But if you go to far northern latitudes or far southern ones, then the horizon tilts relative to you, so that it's harder to see up north. Not impossible, but it's more difficult in the sense that by the time it gets twilight, which is kind of when you can see Saturn, then it's only up 10 degrees above the horizon. So this works, but you got to make sure you don't have like the Transco Tower, you know, sitting here, right? Because then you're not going to see it. Or if you got a lot of big trees or something, you got your favorite big oak tree that's sitting here, that's not going to do it for you either. So you are going to have to go someplace that's going to look, that's going to have a good horizon. And I should warn people, you guys all know this, I'm sure, but it's not going to suddenly look like a brilliant star. So I've seen pictures of like, you know, something like this on the internet, where some hugely bright thing that people are going to, you know, go, oh my goodness, look at that. And it's not going to look like that. But it is going to, I think it looks even prettier for what it is. It's these two objects, beautiful objects, just kind of hanging in the sky like a Christmas ornament. And it's very striking now. It was really pretty tonight with the moon. The moon will be gone in a couple of days, but I think it's pretty cool looking now. All right, so here's my suggestions. First of all, if you have friends around the world, this is visible around the globe. The good thing about Saturn and Jupiter conjunctions is that they're slow. That's why they're so rare, which means that if you miss them by a day or two, it isn't that much different. For here, I would suggest you go find a place where you would watch the sunset. Good horizon is really key. A big empty parking lot, you know, go to the Home Depot or the Lowe's or, you know, HEB or whatever. You usually have a pretty good view of the West from places like that. Athletic field will work, anything like that. And I'll talk a little bit about photography here, about skylines. You're going to have to wait until about 5:45. Jupiter will slowly start to appear, and then about 15 minutes later, you should be able to see Saturn. You won't have more than about an hour before they begin to sink down. In terms of the equipment that you need, this is an event that you can look at just with your unaided eye. If you've got crappy vision, you probably want to bring along your glasses, because once they get close, you might not actually be able to separate them. I think most people will be able to separate them, as long as your vision isn't too bad. And I would say don't give up. You know, if you've got bad weather, you know, keep going on. This is what they'll look like in a telescope. You don't need a telescope to appreciate these. But if you do have one, you should be able to see Jupiter and its moons, and Saturn and its rings, and maybe a couple of its moons. In terms of photography, I know we've got some real expert photographers in the audience. I'll just throw in my 2 cents. I'm not as good as all of you are necessarily on this. But I did take an image of a conjunction between, I work actually with amateur astronomer, avid amateur astronomer, who came to a public night. And we had a public night about this conjunction, but then it got cloudy and everybody left. But then we sort of hung out there, and sure enough, right towards the end, it cleared up. And so we kind of looked around the side of the building and were able to get, you know, he had all the equipment and so forth. So we were able to get a nice photo of this. Then I kind of then fiddled around with Photoshop a little bit to trim it. But anyway, so here's Venus and here's Jupiter, and it gives you some idea as to the sort of thing you can see. I would say that an important thing, if you're going to take images of these things, I would try to have a wide enough field, or wait until they're low enough so that you get some backdrop. Because if all you've got is this, you're kind of going to lose the feel of it, right? You kind of want to have something in the backdrop that tells you where you are. Fortunately, here in Houston, we have some beautiful backdrops, and you still have a few nights to do this. So if you're interested in this, I would get in the car and drive around, try to find a good backdrop, a good place where you might be able to take a photo. And I'd also encourage you to think historically, is that this photo here is maybe interesting in the sense of the conjunction, and also because of the skyline. But it would be even more interesting if you had maybe some cars around here, simply because, you know, 60, 100 years from now, what's going to be interesting about that photo is not necessarily this part. It's going to be what the skyline looked like, and it's going to be the fact that there's vintage cars in the foreground. So, you know, consider the historical aspect of what you're doing as well. As time goes by, I think the event becomes less interesting typically, and the backdrop becomes more interesting. But I like this because it's kind of shows you that there's some activity. It means that this is not a static thing that was going on, that something was really happening at this time in this location. If you take a somewhat longer exposure, you're going to end up with that. So your background is going to begin to come up. So you have to try to decide. Remember, this is now Venus. So Jupiter is going to look like this. So Saturn will be much fainter. So I'm not sure what to tell you as it begins to set. You're going to have to experiment a little bit. If you expose for too long, obviously they're going to trail, right? And there's sort of a rule of thumb, which I'll put here, although people can argue with me about this. I think if you have 200 millimeter lens, you typically want to have less than a 3-second exposure. Otherwise, it's going to start to trail. Likewise, with 40 millimeter, it's kind of 15. You can experiment with that. And I would definitely experiment now with all of that. Pick your backdrop, try your exposures, and see if you can get something good. Just to kind of tweak you a little bit, if you have a good camera setup, and you have like a cable release so that you're not wiggling the camera when you're taking your photo, you can maybe do something like this. So this is the conjunction that we saw for Jupiter on the top there in Venus. And we actually were able to, it was clear enough, we were able to watch it as it was setting. So here's the Transco Tower, I think, over here. The cool thing about this is that it looks alive. You know, your city looks alive. You got something going on here. Somebody is like turning a light on here. So and if I had, you know, parking lots in the front where people were driving around, that would make this whole scene just seem, you know, more real and more active. So I encourage you to use your imagination. Try to find maybe a good spot and try to record this historic event if you're so inclined. And if not, you know, just have fun with it. So I guess with that, I'll end. I've kind of gone over, but I don't feel too bad. I had some questions. So thank you all. And hopefully we'll have some good discussion afterwards.
Well, thanks, Pat. And I'll applaud for everyone, since everyone is, I think people were enjoying it in the chat and then also in the Q&A. So I do have some questions for you if you're
sure
okay with that. Well, normally I would do them in order, but I think there's a couple towards the end that are a little bit more relevant to the viewing aspect. So if you don't mind, I'll ask those first.
Sure.
So again, from our Mr. or Ms. Anonymous attendee, what do you mean by an hour or so until they sink into the haze? What haze is the best viewing time between 6 and 8? I presume if they don't live in Houston, if they're asking what haze, but that's sorry, I didn't mean no.
You're just
no offense, man.
You're slamming H-Town. I don't know.
so I think
yeah,
when is the best time to view it? From what were you saying? Is the best viewing time between 6 and 8 p.m.?
Yeah, here's what you need to do. Here's what I said about the haze, is that if you're seeing this picture here, is that if you had an object that's kind of down here and it's really low, I mean, your skies can get really hazy down here. And that's going to be a problem for Saturn because it's going to look like it gets really, really faint. So you want to try to get them. And anyway, you're going to have trees and buildings and stuff on the horizon. So you can't wait for too long before they get below, you know, 5 degrees or so. Depends on where you are. If you guys are, if the question comes from somebody that's living in Arizona or New Mexico and you got a beautiful horizon and it's perfectly nice and clear, then please come to Houston and we'll talk to you about humidity and haze. But anyway, you know, kind of what you want to do is get on them as soon as you can, which is going to be about 6 o'clock Houston time anyway. So more or less you'll be able to tell, right? Is kind of when it gets dark. And then after that, they're going to move down kind of, you know, this way, more or less. And so you're going to typically have about an hour before they start to get low. Now, for the photographers, you might want them to get low so that you can zoom in if you got a building here or something, you know, and you want the conjunction to be just over the building and you want to make a little movie or something, you might need to wait for them to actually get down there or position yourself so that the building looks bigger. But then, you know, I don't know, you have to figure out what you want to do. But that's kind of what I mean, is that you're going to have about an hour. So from here in Houston, I would say for most locations, between about 6 and 7 is when you're going to be able to get this. After 7, it depends upon how good your horizon is. If you wait until like 9 o'clock, they're going to be below your horizon. They're going to have set. So that's why I'm saying that you are going to have to put in a little bit of effort to see this perhaps, depending upon where you are. I mean, where I'm in my backyard, if I look up now, they just kind of are in the tree line as it gets dark. So I think for the actual event, I'm going to have to move around a little bit to find someplace that's a little bit more open. But it's not terrible. I mean, anybody, I'm convinced that anybody who puts in a little bit of effort will be able to see this pretty well.
So Pat, there's a flurry of activity, and I'm not sure I'm going to keep up with it all. There's a bunch of stuff in the chat. So a lot of them are just complimentary comments about your presentation, and then there's a couple of questions in there. But let me stick on this observing theme for a second, and then we have some more kind of historical and related questions. So first of all, a comment from Professor Patricia Reif, who's saying that the Houston Museum of Natural Sciences will have telescopes out and we'll have a planetarium show afterwards if you're interested there.
Okay.
And I guess you can look at the HMNS website for information for that.
Yeah, and I should point out that I guess the University of Exeter in the UK, although I think it's always cloudy up there, isn't it?
Well, this is in the southern part of the UK. You're thinking of slamming my country, since I slammed your city. Yeah.
Sorry about that. I meant to slam you. Yeah, well, okay. Well, Exeter is supposed to be doing a live stream, and that will.
And we have a race. We have a race person
before ours. So right, if you want to have a preview of what it will look like, you might look at theirs. But it'd be good to have. I'm glad to know that Museum of Science is going to try to do something. Hopefully, they'll have enough of a good horizon so that they can grab it for a little while anyway.
Yeah, Exeter's out in the sticks a little bit, and I think we have a Rice former Rice student there, right? Matt,
yeah, Matt Browning.
Next to yeah. So then we have a couple of questions just about a couple of quick questions about viewing. I think you've said this already, but maybe worth repeating. Darla again, our high school student, is asking. They say it will be seen until the 21st. Is it true? And I think maybe you can.
Yeah, that's a good question. It's actually, I mean, it's ongoing now, right? So if you look at it now, it's maybe, I don't know, 1 moon diameter away. And then as we get closer to the 21st, as I said, it's going to be like 1/5 of a moon diameter away. But all the way up until Christmas, they'll be within a moon diameter. So, anytime between now and Christmas, it's going to be pretty close. And then they will gradually separate. And then, of course, they're going to get closer to the sun. So it's going to be a little bit more difficult to see them over Christmas than it is now. But you should still be able to do it. So even if we have terrible weather between now and Christmas and it clears up for Christmas, you should go out on Christmas and have a look at them. Because remember, if we're looking at how rare these are, if I go back to, I don't know, a typical thing here rather than the records. Yeah, let's look at this. So, anything that's less than 30, even that's kind of rare. I mean, there was one here in 1961, 1901, but a lot of these are really pretty broad. And it's less than 30 for us for quite a while. It's going to be for almost 2 weeks. So, please go out and have a look at it. It's worth seeing, I think.
And then Mark is asking if the angle of Jupiter to Saturn is due west. So is the angle of J to S due west?
It won't be due west. Let me see if I can get the little cartoon up. It's getting kind of messy here. So west, where the sun goes down now is kind of in the southwest, right? And so that's kind of where you're going to see. So in this, if you ignore this part of the diagram, imagine the Houston one just scaled over. West would be over here somewhere. So, yeah, I mean, I can show you this if I exit my PowerPoint and we look at a planetarium program or something. But if you're wondering where to look, all I can tell you is go find someplace you can watch the sunset. And in that general, because the sun will set like here, right? So in the general direction that the sun is going to be, that's where you're going to find these guys. And there's an easy way to kind of figure out the angle. Can you see me on screen now or not?
No.
David? No?
No, we can't.
You can. Okay.
Cannot.
All right. Well,
Oh, no, sorry, I cannot. It looks like other people can see you. So go ahead, do. Oh,
okay. So I have a little demonstration to do for you that might be helpful if you wanted to figure out what. degrees is.
Yeah, I had you muted. That was my bad.
You had me muted.
Well, video
What
muted.
have you been doing
I
the last hour?
I was listening carefully. I just
Yeah,
had
sure
your
you were.
video muted. Anyway, so
Remind
we're
me
going to
to
do the
insult,
fisting.
yeah, remind me to insult Scotland some more when I have a chance. Okay, so, but what you can do, hopefully you're able to see me here. So if you stick your arm out, most people, if you stick your arm out and make a fist, that angle, as you're seeing it, is roughly 10 degrees or so. So, you know, you don't want to like put your fist here or put it way over here, but kind of out in front of you. That's more or less 10 degrees. If you put the bottom of your fist on the horizon and you stack two of these things up, then that's about 20 degrees. And that's about the angle that you're going to see this, more or less. If you want to calibrate, if you've got gorilla hands or something, and they're really short arms, or little tiny hands and really long arms, you can always calibrate just by recognizing that from here to overhead is 90 degrees. And so you just count them, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, or whatever. And then take 90 divided by the total number, and that will tell you how many degrees your fists are. So it makes it really easy to kind of get an idea as to where you're looking if you're unsure. But I think you're not going to have a hard time finding it. You know, just look at the southwest, get a decent horizon. You'll look up, you'll see something that kind of looks like this. It'll be something bright and then something kind of fainter next to it.
All right, so now we're going to test your math skills.
Uh-oh.
Kim asks, how many miles apart will they be at conjunction?
In terms of actual distance.
See how he's hedging?
No, I just want to know what the question.
The only thing I'm working on is how many miles. I mean, I think in the sky.
How many miles? Okay, so they're going to be about, I'll have to do an estimate here, but they're going to be about, I would say probably about 4.8 astronomical units. So let's call that 5. And there's 93 million miles to the sun. So about 450 million miles, something like that.
Right, good answer. Okay, so I'm going to go back. We still have a bunch of questions, and I'm going to try and go back to an earlier one that I deferred from David Warden. So David is asking, does the relative position of Jupiter and Saturn impact climate on Earth by their gravitational tug? For example, does it cause the periodic ice ages, sometimes pulling us closer to the sun and other times pulling us slightly away from the sun? So when they're in alignment and you have these resonances very frequently, does that have a gravitational impact on the Earth? And how might that show up?
Yeah, that's a really interesting question. As the questioner referred to there, we have these cycles in the Earth's orbits, these periodic cycles. And these periodic cycles affect all of the elements of the orbit. So if I can describe to you what the elements of the orbit are, actually my nice little diagram is going to be helpful for you that way. So where's my, yeah, this one. It's getting messy though. Gotta clean that up. Erase pen. Okay, so remember this diagram where we've got the little tilts and so forth. So if you want to specify an orbit, you essentially need 2 parameters for the shape. One of them is what's known as a semi-major axis. And so that's half of the distance, half of the diameter. The other one is the eccentricity of the orbit. And that's essentially kind of how elliptical it is, okay? So, you know, this would be an eccentricity of 0.4 or something like that. Of course, it would actually be an ellipse rather than a whatever I've drawn here. But, you know, the semi-major axis would be half of that. And actually the distances from here to where the focus is, where the sun would be, that's equal to A times E. That's how you define the eccentricity. So there's 2 parameters here for the shape. But now, like anything, if you're going to orient it in 3 dimensions, you now need 3 other parameters that are associated with orienting the orbit. One of them is the inclination, as we saw, which is kind of how much it's tilted. One of them is the longitude of the ascending node, which is this thing. It's the longitude as to where this thing actually pops out of the plane. And then the third thing is something called the argument. So that's known as node. Okay. And then the third thing for this is known as omega, and that's the argument of perihelion. And that's this angle which goes all the way around here to wherever the perihelion point is, where the first point is. And then there's one other thing is that you got to put the planet on the orbit. So that means that there's some sort of time of closest approach. So in any orbital calculation, there's going to be 6 of these orbital elements: A, E, I, node, omega, and tau. Okay? All right, so now the question is, if you're going to actually have cycles for these things, so for example, with the Earth, if you're going to have the eccentricity cycle change a little bit, or the inclination, or the node, or whatever you want to have change, which will potentially affect climate, right? Because if you had the eccentricity of the orbit changing, then it's getting closer or further away, that could affect climate and might influence ice ages and so forth. And likewise with the inclination and with the tilt of the Earth's spin is another thing relative to these things, the obliquity, that can change. That's a different thing though, because it has to do with the Earth spinning, its axis spinning. What you have to then do is say, okay, if I only had 2 bodies, which is like the sun and the Earth, what would happen? And the answer is these things would never change. But once I start putting in these other bodies like Jupiter and Saturn, there's a tug that Jupiter and Saturn and the moon, the moon's going around us too. So you have to add in all these other bodies that are pulling on the Earth. And the question is, if you have those types of perturbations, what effect does it have on the orbital elements? And this brings up something which is known as an oscillating orbital element solution, which means that instantaneously these things have some value. So rather than talking about the eccentricity, you talk about the eccentricity as a function of time. Okay. If you then plot the eccentricity as a function of time, the question is, if you plot E versus T, what sort of thing would you see? Are you going to see something which is just kind of like this? Or are you going to see something which is maybe periodic? Or are you going to see something where maybe it rises or declines? These rises and declines are known as secular variations, whereas these are known as periodic variations. Most of the time, these things are going to do periodic variations if you do perturbations. But each one of these planets, then you have to put in and do the perturbation. And the interesting thing is, it doesn't matter so much if they're lined up, because these perturbations act over the entire orbit. So the way that this is actually solved in a celestial mechanics kind of way is you take the mass of Jupiter and you spread it out in a big ring. And then you imagine having that ring, and then you spread all the other planets and you see how they actually perturb the Earth's orbit. So you can imagine that this is a very difficult, talk about calculus, huh? This is a very difficult thing to do. And nowadays, of course, solving these equations is, you can't do them analytically, really. You can do perturbation analysis on them. You can't really do them analytically. So you throw them into the computer and you hope that all the solutions actually converge. There's this weird thing that happens, which is numerical chaos, where you can start out an orbit with a very, very similar kind of initial condition. But if you're in a chaotic part of the orbit, you can actually then have these solutions diverge, which is one of the ways in which you can actually create gaps, for example, in the asteroid belt. All right, so anyway, so that's kind of a long answer, but you asked for it. So that there are these complexities associated with orbits. If you want to do these well, yes, these orbits, in fact, these planetary perturbations do matter. Jupiter's and Saturn's perturbations do matter on the Earth. Less so than you might think, because the Earth is zipping around a lot, but they do have some effect and they have to be included. I think that most of the Milankovitch cycles, though, aren't due to Jupiter, but I'm not entirely sure about that. I think that some of them are lunar in nature, but you have to look those up and see. But I wouldn't be surprised if Jupiter has some effect, because it's big, right? And it's got pretty big gravitational force. It's yanking stuff around.
Apparently Google hates a search on osculate. I'm not sure what that means, but we'll skip that a second. So I think Mark Ulrich is still on. So he asked a question way back. 1226, the year of the last best JS conjunction, was roughly 794 years ago. Question: do multiples of 794 years also translate to other good conjunctions? And then he throws in some numbers. So
welcome to my parlor, right? Yes. All right. So that goes back to this whole business. All right. So this 790 thing is kind of close to the separation between these series. So the answer is roughly yes. It has to something to do with these 800 series. Isn't that like the 800 series is like some money thing or something? I don't know. Anyway, so let's look at this here. So this is my 854 year cycle. So let's see if he's right with that. I got to figure out how to clear this better.
Erase pen, yeah.
Erase pen. Yeah, Shift E. By the time this is over, I'll know what to do. Okay, so let's look at this. So this is my 854 year cycle. So these are all separated by exactly 854 years. But if we now look at this one and compare it to 1226, that's his 790, whatever it is, right? So actually what you're doing is you're comparing two adjacent 854 year cycles. So we now ask ourselves, how are they adjacent? Well, they are adjacent because they have roughly the same longitude. Why do they have the same longitude? They have the same longitude because they are separated by 60 years, which was one of our cycles. But you notice all of these are negative and all of ours are positive. And that's because when you go a 60-year cycle, you change from the morning to the evening. So yes, they are related, but they're adjacent in parallel cycles, if you will. And actually, that's how I was able to figure this stuff out, is that you notice that these cycles kind of go through a minimum and then there's a maximum again, minimum and maximum. It's because they don't line up perfectly. I mean, Jupiter and Saturn don't care about me and my 854 year cycle, right? They're doing whatever they're doing. And if things are off a little bit, you know, these things will begin to kind of shift. And so what I would do is that once I started to get up to like 4583 or something, I'd say, okay, this one's starting to get no good anymore. Where's another one good to start? And I would pick one then that's, you know, 60 years away from this one. And so then I would go find this one, which is 4523, which is 60 years away. So these things are all kind of linked to one another. And you can walk yourself up and back in time that way and make sure you don't miss anything.
So yeah, if you happen to own a clock store, you can just set each clock a different couple of minutes faster, and then just watch them for the next several years and see when they all, how many line up and when they line up.
That's
right?
exactly what this is. And in fact, if you want to send some money to my PayPal account, maybe I'll predict your future for you while you're at it.
He'll also send you a Mickey Mouse watch with a moon dial on it. Anyway, okay.
Yeah. Does that go forward? Does the mouse hands go backwards?
We're supposed to be the serious people here. There's some good questions coming up. So let me Stephen Baker asks, how bright are the moons of Jupiter compared with the brightness of Saturn? Should I be able to see them with my binoculars?
You should be able to see the moons of Jupiter. They are about 6th magnitude or so, which is right at the limit of being able to see them with the naked eye, maybe 6 or 7 magnitude, something like that. Saturn is, I don't know, it's about 0 or so. So it's pretty bright. Jupiter is like minus 1.5 or something like that. So yeah, you would have no problem seeing Saturn, and it's way, way brighter than Jupiter's moons. In binoculars, you should probably be able to see Jupiter's moons, depending on how good your binoculars are. A small telescope, you will definitely be able to see Jupiter's moons, and you should be able to see Saturn's rings, also a small telescope. So the way in which it usually goes is that if you look in binoculars, you can see at least some of Jupiter's moons, maybe all of them or all 4 of them if they're spread out. But you usually can't see Saturn's rings. And then once you up the aperture from a binocular to a telescope, then you begin to pick out Saturn's rings. And then after you pick out Saturn's rings, you kind of begin to pick out some of the moons of Saturn as well. Moons of Saturn are fun because they're kind of spread out in brightness. Moons of Jupiter are all kind of equal brightness, more or less.
Thank you. And then Anne Arnott asks, does the amount of man-made light in the sky now make a difference to our sight over the history of the conjunctions?
Yeah, no doubt about it. It's far more difficult now to observe these close conjunctions, you know, the ones that are right next to the sun here, like this one. I guess these are not very easy to see. Do I have the angles? Yeah, that's this one. So let's pick this one in 1285, for example. That one's 20 degrees away. In order for you to be able to see Saturn, you'd be able to pick out Jupiter from that pretty easily. But Saturn would be tough because you have to wait for the sun to kind of set enough. And then you got to be able to pick out kind of a faint Saturn. And that's not that easy to do. It certainly is a lot harder now than it was back then because you have this huge glow. Because, you know, not only do you have the sunlight reflecting off particles, which you always have, but now you've got all the man-made glow, which gives you this light pollution, which makes it difficult. One thing that I will say for this event and what this event has going for it, over like looking at a comet or a meteor shower or something like that, comets and meteor showers are notoriously difficult from inside of a city because the background light can really cause you problems. It makes it difficult to see the tail. It's harder to pick up faint meteors, etc. But here, the objects are pretty bright. I mean, most of the time, you're not having any problem seeing Jupiter. And Saturn, as long as it's not too low in the sky, you should be able to pick that out too. And so the good thing about this is that you can actually see this from the city. So it's a good city event.
Okay, so so Pat is saying show my picture from last night and make sure that well, it's helpful to have your binoculars on a tripod. Pat, I'm not sure if you're just referring to everybody with that picture. I just checked my email. I don't know where to find that, so I can't show it. But I guess what Pat is saying is that from Houston, from downtown, essentially in West U, I think, well, she's on a ranch. She basically took a picture using binoculars, and I think it must
Yeah,
be
she sent that to
quick.
me. I don't actually have it included in
Oh,
here.
okay, I don't have it, so I can't share
It
it.
looks
So
quite nice. I mean, the point is that you are able to see a very pretty sight now. Certainly
right.
from my house, which is out in Manville, which is south of here, about 20 miles. I didn't trust the internet, so I came into Rice. There, it's real easy to see. It's so easy to see that I can kind of stay inside and look through the window. It's like, oh yeah, there it is. But it's much more impressive, obviously, if you go out. To me, this is really starting to just get impressive now. It's starting to get to be close enough that you look at them like, wow, that's cool. It's almost like they're a little unit together moving.
Okay, so we have a couple more questions, Pat, and a couple of them are quite are detailed and a couple are quick informational. So let me again just read them in order. So Greg Leroy, let me just check. I'm not sure if I should ask the question unless they're still on.
I know him. I know him well.
Oh, and Greg is still on. So that's good. So let me ask Greg's question. There are excellent predictions for these planet movements for plus or minus 3,000 years, but beyond that time frame, much less certainty. Can you generally explain what factors in celestial mechanics provides that uncertainty beyond 3,000 years?
Yeah. I mean, obviously, one of the things that goes into them is what the errors are in the positions of where you're seeing the planets. The other problem is just in the numerical simulations, the numerical round-off errors. If you're trying to get stuff which is really, really precise, it can be hard to make sure that your code is doing what it's supposed to be doing. My sense is that that it's more the measurements than the codes, but I'm not sure because I don't actually do the codes. But I think we have somebody on here that does the codes, so maybe they can answer that.
Now, one reference point, I came from a group in Glasgow who spent hundreds of years doing celestial mechanics and stuff. And the challenge was they managed to, and it may have changed in the last 30 years, but they were able to get the solar system doing all of these calculations to be stable for 1 million years. And we know, of course, the solar system's been stable for about 4.5 billion years. So these calculations, when you add up all these little perturbations, are just really, really difficult to do. You have two-body problems that are easy, some specialized three-body problems that are doable, and then you have large number of body statistical approaches, and then anything in between is really, really difficult. So um, I just think it's just really hard as soon as you add these things, and then you have them tiny, tiny little changes accumulating over time, and then they all feed off of each other. And
Exactly.
we don't do that at Rice, but it is hard. Astronomers are smart people, right, Pat?
Yeah, let me give you some context for that, actually. So this my little cute thing here with all the planets. So when I first did this, I didn't get any of these things lining up. They were off not by a lot, but maybe by 4 Jupiter diameters or something like that. And so by going to the fancier predictions, it will shift these things around by several Jupiter diameters.
So
And
that was a question about this picture, Pat. A couple of people asked it, and I may have answered one of them incorrectly then. So Karen, and I think Robert as well, but Karen is, and we know Karen from old. Karen was saying, a very fun talk. What software did you use to get the photos predicting the look of the far, far future pictures, which I think are the ones we're looking at now? Was that done by hand, or was a piece of software for the?
oh, no, this is all part of Stellarium.
Okay.
Although there's a module in Stellarium that you can grab the far future and far past ephemerides. And those are the latest JPL ephemerides and putting them in there. So I will say that I haven't done my own calculations on this to try to verify if Stellarium has any errors in it that are associated with this. I can say that I've used Stellarium a lot, and that all of the answers make sense to me, but you would probably actually have to go through the actual all of the perturbation equations and so forth, and it gets to be quite nuanced to do that. So it's not like I'm doing this for publication necessarily, but if I wanted to, then I would have to go back by hand and do all these calculations myself just to verify that there wasn't some coding error somewhere. But as far as I can tell, they've done a really outstanding job, these guys.
So Pat, I'm going to leave Darla's. There's three more questions. One's about. I'm going to leave Darla's for last.
Okay.
But there's a question that was in the chat from Tammy Moffat, who's still also online. Let's say you live in Washington State in the Pacific Northwest. Dusk is at 4:30 p.m. right now. What would they expect? How would they go out to look at it?
You go out, you do the same thing that I'm describing here. Is you go out at dusk. You look in the direction where the sun went down, and you should have a beautiful, view. Pat Rife sent me an image that a photographer friend of hers took over the ocean, and it was a beautiful shot of the ocean with the conjunction over the ocean. So, although it's cloudy a lot up in Washington, but if you have that, basically you go out and you look in the same direction that the sun would set, and you look about 15 degrees up. It's going to be lower for them because the angle isn't as good. So you'd have maybe, it'd be 10 or 15 degrees up as opposed to 20, which is what we have. So it's going to be, they're going to have less time to see it than we will. But it's the same idea, is that you go out, you find some place where the sun is going down and look in that general direction as soon as it starts to get dark, and they should be able to see it. And I would really recommend, if either you're living up there or maybe your parents or some friends are, tell them to go out now. I mean, don't wait for anything. If it's clear, go out and look in the southwest, because you should be able to see Jupiter, and that'll help you, get more of a scale of what you're supposed to look for too.
Tammy says thanks, she's on it. So I think that was good. So Dan Herman says, do your orbital models account for general relativity? If so, what sort of impact does it have on the timing?
No, I don't think that any of these things have GR corrections in them because they're too small to matter. Your GR corrections only matter when you're in a very, very deep gravitational potential well, and these things aren't that. So I doubt that these things have GR corrections in them. Although, I mean, we could look up the actual paper. I think it's a 2014 paper, and we could see if they put in GR corrections. Sometimes they put in some pretty interesting other things, though. For example, light travel time. So it actually takes a little bit longer, for example, in this picture, for light to get to you from Saturn than it does for Jupiter. And so if you really care about whether or not this is 1100 UT or 1115 or something, you actually need to take into account the fact that there is a delay in the light travel time between these planets. I think Stellarium has that in there, but I'm not sure about the different ephemerides, what they do with that. But generally, GR is usually not an issue for these types of things because the perturbations are too small. You might worry about it with Mercury's orbit or something like that. But
yeah, I wrote a paper on the three body problem with general relativity back in 1988, and it's been cited like maybe 2 times. So nobody's interested in
well,
this
not
stuff.
3 now.
Yeah, getting the plug out there, you know. But I think I looked at it a few years ago, and I don't understand it anymore. So I'm sure it was pretty good at the time. Anyway, big final question from Darla again, our high school student who's been asking questions away. And you can answer this in any way you like and in any units you would like. How many years have you been studying this?
If I can use any units that I like, then 1, right?
The question is, have you been studying this your whole life? And the answer is not yet. Right.
Yeah, not yet. Yeah, exactly. No, I'm one of those people that's kind of more increasingly rare, I think, in astrophysics these days, in that I was a amateur astronomer as a kid. So I've been kind of studying the sky since I was 8 years old, more or less. And, you know, if you really want to get into astrophysics, and do it as a career, you know, as a profession, you do need to spend and really enjoy doing mathematics and physics, because ultimately that's what this is. But I do have that connection to the amateur part of it, and I know what it's like to be out there in the cold looking through a small telescope. I'm one of the people that back then was making visual observations of variable stars. You know, I've worked with the primitive CCDs, everything from small spectrographs up to really big ones. I've worked on some of the largest telescopes in the world, you know. So I've gone a lot of places using a lot of different types of instruments. But I think what helps me with this particular thing is that I do have that amateur background, so that I kind of have a sense as to what is going on in the sky. And a lot of astrophysicists these days tend to be more, you know, mathematician and physics and computer oriented. I think there is some aspect of that, of this, of the sky that is helpful to know, because at some level, I think it provides you some perspective in that like when I go out before dawn and I'm walking my dogs, for example, I look in the east and I look at the constellations and I see Ursa Major and Arcturus rising and so forth. So I know that spring is coming. Now, intellectually, of course, I know that spring is coming. You all know the spring is coming. But, you know, there's some being able to actually sense that all the time, because I always have a sense of kind of where the planets are, where the sun is, and how everything is moving. I think that it's a great hobby. It will enrich your life in a lot of ways, even if you don't go into it professionally. So for all of you out there that are sky watchers, I give you all a thumbs up. And I think it's this sort of thing is like this conjunction is something that we can really all enjoy together.
Yeah, and I think that also explains why you never let me near the Rice telescope. But anyway,
Yeah,
I also presume
there's like no way.
I also presume you know when winter is coming, but that's a little cultural reference. So listen, Pat, it's been fantastic. And someone just asked if the recording will be available. We usually make them available. We have a Rice Space Institute YouTube channel, and we'll make sure we get that recording up. We might try and delete our earlier conversation before we knew we were live, but
well, I think you're more in trouble with that than I am, aren't you?
I'm not sure what I said, but I'm sure I said something wrong. But no, listen, we'll make that available, and appreciate everybody's time. I think we had 140-ish, or a little bit less than 140 people at max. And Pat, that was
Did
really,
they all
good.
disappear when I got to the complicated equations part? Or?
I think it was just when you got past the hour and a half, maybe. But I think no, I think it was. I think people really enjoyed it, not from the point of view understanding what's going on and the way that it was explained. I think a lot of people were commenting on how understandable you made it, and I think that's really important. So I think everybody thoroughly enjoyed it. And Darla, our high school student, is from Mexico, and she wants to know how she can contact you more. Look on the website Rice, physics.rice.edu, and you can find Professor Patrick Hartigan. And Darla, keep watching the skies, as Pat says. So, and thanks for being part of this. So again, thank you, everybody. Enjoy your holidays. There'll be another set of Rice Space Institute Frontier Lectures in the spring. I'm still working on that, but take your eyes to the west just after sunset in the next few days. And again, stay safe, stay healthy, and have a great time over. Hopefully, you have a break. And Pat, thank you again. That was fantastic.
All right. Thanks, David. Thanks, everybody. So long.
See ya.